Okay, now finishing the rest of chapter 3 in our workbook on applications of differential equations, we're going to finish off first of all with section 3.6 on falling bodies and air resistance. So remember from section 1 of the workbook, we looked at very simply Newton's second law as a differential equation. And so what we're looking at here is a building, looks like the Leaning Tower of Pisa, and we're tossing a rock off the top of it. And we're very interested to use a differential equation to describe the position of that rock as it's falling. And it's in many cases in applications, it's important to have a good frame of reference. And so what we're going to do is, what do we mean by position in this sense, and what direction is positive or negative? So it's illustrated here in the diagram here that we're going to look at a vertical axis here as representation how the position of the rock as it falls. Position 0 will be the ground, right? And then we're going to initially throw it from the top of the building, which will be a position, let's say S sub 0. And so the idea is that, moving upward is positive and moving downward is negative in terms of moving in terms of those directions. Upward direction is positive quantity, downward would be negative, right? And so Newton's second law in this particular case can be represented simply as the mass times the acceleration, which is the second derivative of the position function s, which is minus mg, or we could just divide through by the mass, and we simply have this differential equation, all right? So to build an IVP for it, though, we need to think about, all right, initially we're given information about where the rock is. Initially is at the height of the building, which is position 0. And we're also looking at the case where we're tossing it initially upward with a velocity v0. So that's why that would be positive. If we're throwing it down from the top rather than tossing up, that would be a negative value for the initial velocity. So now what I've done here is I've shown you that and indicated in the notes, don't worry about this. It turns out the solution or the position function that derived from solving the second order differential equation is given here. I'm going to go ahead and derive it for you because it's actually, it'll be helpful perhaps as we look at problems this Friday, as well as some problems in the WebAssign. So let's look at this second order linear differential equation, which just says the second derivative of the position is given by minus g, all right? The gravity force acting on the object represented by a negative quantity, all right? All right, so if we were actually trying to get s from this differential equation, one approach would be, well, why don't we just start integrating both sides? And we integrate with respect to t. Well, if we're integrating the second derivative, that would produce the first derivative, just fundamental calculus there. And if we did this integral minus g dt, we would get what? Minus g, t is the independent variable time, and then we'd add a constant c1. Well, if we want to get s, we'll just do this again with respect to integrating by t, and out would come the position function s. And then by these integrals, we would have minus g quantity t squared over 2 plus c1t plus another constant c2. And we would have a family of solutions to describe the position. But we know specifically how we're tossing and where we are when this rock is released. In fact, we know that initially it's at position s0. So this value s0 represents the position at time 0. So if we plug in t for 0 into this equation, we'd have g over 2, let's say, 0 squared, plus c1 times 0, plus c2. Those quantities would go out, multiplying by 0, and that just says, in fact, that the second constant is your initial height, which is what we have here. Similarly, we know we're tossing it initially, and that is the velocities at v0, and that would represent the derivative of the position at time 0. Since we have the position function there, if we were to compute the derivative over here, for example, s prime of t, that would be what? Minus g, 2 squared would be 2t, so we would just get minus g t plus c1, because the derivative constant 2 would be 0. So then what we would have here is when we plug in 0 for that derivative function, we get minus g times 0 plus c1, So in fact, this is nothing but 0. So this says that C1 is the initial velocity. And that's what we have here. So that fully determines this quadratic equation that describes where is the rock at time t, knowing that eventually it'll hit 0. And if we want to know when it hits 0, we would set this equation equal to 0 and solve for t, right? But let's look at adding a little bit more reality to the model. And this is what you do in the physics and then resulting change in differential equations. Well, a bowling ball would drop differently. The rate, when it would hit and would be different than if it was a tennis ball or a rock. So let's include air resistance. And typically that's a force represented as proportional to the velocity of the falling object. And that can be done by a term like this, minus kV. That K is sometimes called the drag coefficient. So let's just go in the next page and go ahead and modify our differential equation. So in this case, we will modify Newton's second law to be the following. Mass times the acceleration, or we'll write it as the derivative of velocity, is mg, which we had before, minus kv. And that's why we represented the left-hand side in terms of the derivative of v, because the air resistance is given in terms of velocity. So here we have a differential equation in the dependent variable velocity. But we really are interested in knowing what the position of the rock is. So again, we assume that s of t is the distance, or position, is the distance, we'll say, the body or the object, body/object, falls in time t from its initial point of release. So what we have is that, of course, velocity is just the derivative of the position function, and acceleration, of course, is the derivative of the velocity. So relating those two, that, of course, is the second derivative of position. So by substitution, we can change the differential equation in the velocity to a differential equation in position. In other words, by substitution, we have the following, that m times the second derivative of position with respect to time is equal to mg minus k times ds dt. And then maybe pulling the derivative terms over to the left, we have the mass times the second derivative plus k times the derivative is equal to mg. So in fact, this is a second order linear ODE that describes the motion of the rock or the body of the object as it falls, taking into account air resistance. So you get a different equation, different kind of solution, right? Let's look at another nice example in suspended cables. This comes more from civil engineering, where you're looking at keeping a cable sort of nice and stable as if it's suspended between supports, vertical supports like a telephone wire, suspension bridge. And what we're really interested in is how it sags or hangs at its lowest point. Okay, that's what we're interested in here. So geometrically, we could redraw, in a more generic sense, a Cartesian coordinate system representing that portion of the cable or the wire. And here's the lowest point, P1, and then we go up a little bit higher up from that on the cable, P2, and look at sort of the forces acting on the cable at those two different positions, all right? Or in the case of the, gravity acting on it with the weight, say W, all right? It's a portion of the vertical load between those 2 points. So the idea here to notice is that there's tension, T1 and 2, that are actually represented by tangent lines at P1 and P2. So you can see the tangent here at P2, and you can see the tangent here at P1. So and notice that the tension at P2 has been broken into two components, right? So let's notice that the tension T2 has horizontal and vertical components, which are in fact T2 cosine theta and T2 sine theta, we'll say respectively. In fact, here's the horizontal. You can see that from the diagram. That's the horizontal component to the tangent. And then here is the vertical. So that's interesting because if you think about what we know about derivatives, right, the slope of a tangent line is the rise over the run that describes, what that slope of the tangent line is, right? So if we want stability in the system, or maybe referred to more specifically as static equilibrium. So for static equilibrium of the cable, we require those opposing forces in those dimensions to balance. In other words, we would force T1 to be the same as the vertical component of the other position P2. So that would be T2 cosine theta. And we'd want that vertical load, or the W, to be the same as T2 sine theta, which is the portion of the tension at that other point. So that's what it means to be in equilibrium. And if we do some algebra here, you can show that, well, that says that T2 has to be T1 over cosine theta, solving that one, which also would have to be the same thing as W over sine theta. Okay. And in fact, if you took sine over cosine there, you could show that, well, that says the tangent of that theta angle in the picture would have to be W over T1. But we know something geometrically. We know that, in fact, tangent, which tangent theta would be sine over cosine there, would be the same as the derivative at that point, right? Which is given by dy dx. In other words, the derivative is always the slope of the tangent line. Okay, this time it would be at P2, of course. So in fact, this is a very simple first order linear differential equation. The derivative for static equilibrium, you must have this happen. The derivative has to be W over T1. This model doesn't take into account that, the shape could change, distort for different physical reasons through time. This doesn't take that into account. That's typically what happens in a dynamical system. But, this is a very simple way of at least representing with a nice geometric argument how a differential equation can be used to model the shape of an object, in this case of a wire. Let's finish out by looking at, again, looking at series circuits that we've talked about before, but specifically, what are the differential equations that relate to the different types of circuits? And the first one is just doing an LR series. Remember, L represents inductance, R represents resistance. And we're looking at a very simple circuit where we have an electromotive force, E of T. Now, that could be a battery. We have an inductor representing a coil with inductance L, and then we have just a simple resistor. Resistances only absorb energy. They're like the heating coils and things like that in a heating unit. Inductors can store and deliver energy. So that's, and they do it using a magnetic field, which is what Michael Faraday showed. So again, this is an inductor, and this is a resistance or resistor. And so it turns out, very simply, using what Kirchhoff's voltage law, which I think is covered to some extent in the EF courses, we can represent how the current um, changes, or at least the relationship of current as a differential equation in this series circuit. In fact, all it is this particular equation. In other words, that L times di dt plus Ri equals E of t models the current flow, or the response, sometimes they say, of a circuit. So if you know what the value of L is, you would plug that in. If you know the value of R, you plug that in. And then, E of t could either, represent an AC source, or it could be a DC source, which is a battery, and you just represent the voltage. Another option is maybe you only store energy with a capacitance. So you'd have your energy source, your electromotive source here, and you would have a resistance again, R, but then you would have a um, you would have a capacitor, right? C there, right? Again, storing energy by the separation of two charged plates using electric field. In this case, though, rather than modeling current, you're modeling the charge. So Q in this case is the charge on the capacitor. And you would simply plug in the values R and 1 over C times Q and set that equal to whatever the voltage source that you're getting. Could be a constant, maybe not. Could be a sine or cosine function related to it. And what you have here is just a simple way of determining, ultimately how much power you're going to be able to have in the system. Power into that resistance in terms of, how much heating you're going to get, how much energy absorption you're going to be able to get from the E of t, as well as the energy source, as well as the capacitor. So a little example to finish out, let's just go back to the case of an LR circuit and plug in some values. Suppose you have a 12-volt battery source, you have a 10 ohm resistance, and you have a inductor of 1/2 Henry. Okay, and so in this case, L, the inductance coefficient is 1/2, and the resistance coefficient is 10. And so the model is simply this. Again, I'm not asking you to derive it, just understanding that it is easy to just take values and plug them in. We have 12 volts for the electromotive source, which is constant. So we'd have 1/2 times di dt plus 10I equals 12. And then just simplifying this, we could get di dt plus 20I equals 24. And again, this is a linear first order ODE that models the current in that series circuit. Initial condition, we might have that we initially have no current. Later on, we will come back to this kind of a circuit problem and look at the differential equation that describes the current and determine how the current behaves through time as time marches to infinity. Next up is just understanding properties of solution curves and starting methods that actually we can use to solve first order and second order differential equations.